All right, welcome to the last lecture for Coco this semester. My plan for today is to finish talking about the memory content first. Then I will go over a finite state machine example. Then I'll finish up today with talking about some of the content that is going to be important for the final exam, the logistics, the timing, things related to the final exam. So I'll do those three things. In terms of announcements, there's just one, homework 12, that is outstanding. That's due tonight. So please make sure that you submit that. There's no daily quiz today, so you guys don't need to worry about that. No daily quiz today. I think it's good to stop at 25 quizzes. So we'll stop at 25, like I said in the last class. I also want to encourage each and every one of you to perform a thorough check of your submissions and grades on Gradescope. So sometimes what happens is the person who is submitting a studio forgets to add their partner to the submission on Gradescope. And in that scenario, their partner would not get the grade, the appropriate grade for the studio. So make sure that both partners are linked to your studio submissions. So make sure you do that. Do that this week, so that when I export the grades from Gradescope, I have everything correct, and I don't have to, you and I don't have to worry about going back and changing grades and so on. Also, I would like you to request to you guys to fill out the course evaluations. The course evaluations are pretty important to refine a class, especially now that we went through this entire course online. It is very useful for me to know what worked and what didn't work this semester. So we had online lectures and studios with TAs on WebEx Teams, with you guys operating the Basis 3 at home. So there were lots of things that were new, because we have never done a completely online class for Coco for this magnitude, right? Over 100 students. So I would like to know what worked and what didn't work, so that I can make the appropriate adjustments next semester. There's a question online. Some homework grades and studio grades are not available on Gradescope. Will they be available before the final? Yes, that is what we are aiming for. So there are a couple of homeworks the TAs are working on. They have not finished grading that yet. They have made progress, but they have not finished it yet. However, I still want to encourage you guys to check, especially the studio submissions, right? Because two people are attached to one submission. Make sure both the students are there. Of course, if your partner has worked on it alongside you. So that I don't want that to fall through the cracks, the studio submissions. Any other questions about the things that we just talked about? Okay, let's continue our lecture on memory. We were talking about the internal structure of a ROM. We first used a 3 to 8 decoder here to make sure that only one of these outputs is active at any given time. So the user enters an address, a 3-bit address location. And what happens based on that is one of these outputs is going to become active, which is going to make that a low level for one of those vertical lines. And then if we connect them to output buffers, that's what we read, D0, D1, D2, D3. And the reason why we are doing this inversion at the end with output buffers is because we want to map the zeros and ones based on where the diode is present and where is it absent, right? So an absence of a diode will reflect as a zero as the 4 bits that are the output bits at that particular address location. The presence of the diode is indicated by a 1. Another question online in the chat box: are all the quizzes going to count, or will one or two of our lowest quizzes will be dropped? I've not gone through the grades yet, Jason, but I will drop a couple of lowest quizzes. Yes, that is my plan, because initially some students missed it, so I'm going to go through. I've not really decided upon how many to drop yet, but yes, that is my plan to look into that. Preston says, I'm a bit confused on how the diode is interacting with the wires. Well, the diode is essentially interacting as an interconnection between the horizontal and the vertical lines, right? So if this guy is low and that guy is high, and if you have a diode present over there, you see at the anode of that diode you have a positive voltage. On the cathode of this diode you have a negative or zero voltage, a low voltage. That is going to make that diode on, right? It is going to be conducting now, which means this point, this particular line is going to have the same potential as low, as opposed to if both the ends of the diode are at the same potential, then the diode is going to be off and no current will flow through that. Essentially an open circuit, which means these vertical lines are not going to be connected to these horizontal lines, and hence they will read high. Does the final be cumulative or just the content of after exam 2? It is cumulative. So the horizontal lines connect to ground, not all of them, right? So that would depend on what the 3 to 8 decoder outputs, right? So if we gave an address of 101, that made this guy active, Y5 active, and what active means is because these are active low outputs, that is low and everything else would be high, right? So that is not connected to ground, it is a low voltage, a low level. Right? So which one is going to be low depends on the address, and only one of them can be active at any given time. So only one of them can be low at any given time. So how would it bring down a high wire? So you see this? If I have so this wire right here, the highlighted in pink, right? That is low right now. On the vertical line, I have a vertical wire that is connected directly to high voltage. And when I have the diode that is on, you see this wire and that wire are going to be at the same potential, because all that 5 volts from here is going to be dropping across that resistor right there. However, if the diode is open, then this wire is directly connected to high and it would hence read high. So essentially that is a simple cross connection. If you had that diode present and the diode, what is important is what are the two voltages at the two ends of the diode. So if you have, for example, +5 there and +5 here, the diode is open, right? And there's no connection there. However, if this guy is 0 and that guy is 5, that means that this diode is not now conducting, which means this is going to be connected to that. That only happens if Y4 would have been low. All right, let's see. So here we were using diodes. And this was one-dimensional decoding, right? It was one-dimensional decoding because the size of the ROM here is 8 by 4. The reason why it is 8 is because we have 3 bits as the address, so 2 raised to 3 will give us 8. That is your number of addresses and number of rows you can have for the different number of rows in your memory you can have. And at each address location, you have 4 bits, because the moment you enter a 3-bit address here, you will be able to read 4 bits that are stored at that particular address. That's exactly what we are doing. We are going to replace diodes, which consume a lot of power, with transistors. That's coming up later in the lecture. All right. So the previous example was about one-dimensional decoding, but what if you want to have two-dimensional decoding in a ROM? So this is an example in which we are still using a 3 to 8 decoder. We are also using a 16 to 1 multiplexer, and we have array of these diodes arranged over here. That the arrangement of these diodes, specifically the presence or absence of the diodes, is going to make the memory have a 1 or a 0 at that particular location. So what the best way to analyze this structure is to first talk about the size of the ROM. This is still a ROM, right? Because I'm giving it an address right here, and I will read the data at that address in D0. So it's still, give me an address, I will tell you what is at that address. You're not writing anything, you're just reading from the memory. So it's still a ROM, and the first thing we'll do is we'll talk about the size of the ROM. So what is it going to be? 2 raised to 7 by 16. All right, so 2 raised to 7, let us see if that is correct or not. That depends on the number of address bits, right? So we got A0, A1, A2, A3, A4, A5, A6. So those are 7 address bits. So 2 raised to 7, I agree with that. By how many bits are stored at each address location? Remember, this is one-dimensional decoding. Two-dimensional decoding, right? So it's 1 bit. Yeah, absolutely. Right? You're getting 1 bit. So this has to be 1. So the size of this is 128 by 1. That's the size of the ROM. 128 different addresses, and at each address you have 1 bit that is stored. You know, an easy way to understand this is whenever you have a two-dimensional decoding situation, you will have 1 bit that you will be able to access or read. All right. The next thing we'll do is we'll pick up some arbitrary sequence. Let me say I want to read at what is stored. What is stored at, let's suppose I say 7E in hex. So I've given you the address location in a hex format, and I want to find out what is stored at that particular location. So which bit, right? It's going to be just 1 bit. So the first thing that we do is we write out 7E in binary. So that would be what? 0, 1, 1, 1, and then E would be 1, 1, 1, 0. Right? So we have got all of these bits. That's our address location. Next, we will try to write A0, A1. Those are our address locations, right? Those bits map to those inputs for address. We, of course, don't have A7, so we don't even need to worry about this. We only have A0 all the way to A7. So everything is 1 except for A0. So let us write that out here. This guy is 0, 1, 1, 1, and then everything else is 1, right? So that's our address location that we are trying to read. Now, once you see A4, A5, A6 being a 1, Can you guys tell me which particular output is going to be active in this case? You have output 0 all the way to output 7, right? So these are your outputs. Only one of them is going to be active. Right now, A4, A5, and A6 are all 1. Which output is going to be, right, 7. So 7 is going to be active. So what I'll do is I will highlight 7 horizontally. So that is active. Everybody else is inactive. I ignore everything else. Next, I have A0 as 0 and A1, A2, A3 as 1. So in terms of, so those are the select lines, right? The A0 to A3 are essentially controlling S0 to S3. Those are the select lines. And these are your data inputs. And a multiplexer takes in many inputs and allows one to pass through depending on the select lines. So the select lines are 1, 1, 1, 0. So which of these inputs is going to be read? 14, right? 14 is absolutely right. So let me highlight 14 here. Okay, so based on this, again, you see, why is it called two-dimensional? Because you have got a selection on rows and a selection of columns, and hence only one bit. Now, if this guy is low, right, this is low. What happens to this particular diode? Is it on or off? Because on the other end of that diode, you have a plus 5 volts connected through a pull-up resistor, and on this line you have low because that is active. So the diode is on, absolutely right. So if the diode is on now, what are you going to read on this particular line? A low or a high? Low, right? So that is low, which means after it goes through this bubble right here, that is essentially inverting the bit, what do you have after that? You have a high over here, right? And that high is what is getting selected. So D0 is going to be high or 1 in that case. You see that? Yeah, so low comes in over here. However, that bubble inverts it, makes it high. So the multiplexer has inverting inputs in this case. We did a similar thing here with output inverting buffers. Over here, we are doing a similar operation by using a multiplexer with inverting inputs. So what does that result in? You see, the presence of the diode means that you have a 1 stored at that location. If you chose something like this, that particular location, it's not present, and the data stored at that location would have been 0. You guys see that? So presence of the diode in this particular arrangement indicates that you are storing a 1 at that location. So the point of the diode is to essentially divert. So the point of the diode is essentially to turn on or off based on which of the output of the decoder is active, right? So because it's a decoder, only one of these lines can be active. And on the other side, the anodes of the diodes are all connected to plus 5, right? So on one end, plus 5 is already connected. On the other end, it can be plus 5 or it can be low. When it is plus 5, you have both ends of the diode at the same potential, meaning that diode is open and current is not going to flow through, which means that the vertical lines will be now high. However, when the cathode, the negative terminal of the diode, is at low potential with respect to the anode, then the diode is on and the vertical lines will now read a low voltage, which we can then flip by using the inverting inputs of the multiplexer to make sure we read the appropriate data. Embedded software. So that is, related to transistors. We would not be using high power consumption diodes for doing this. This is just to indicate the structure, but we can replace diodes with transistors, which are, very, very small in comparison and consume much less power. And that's how we are going to be storing the bits. All right, so I hope that this two-dimensional decoding, the ROM structure, you guys, for any given address location, you guys will be able to find out what is stored at that particular location, and also this is not programmable. Yeah, the diodes are hardwired. If they are hardwired, then they are not programmable. All right. Today's ROMs, however, have a much larger size, right? 256K, 1 meg, larger. We are talking about a really, really big ROMs nowadays. So what we do is, instead of using diodes for the cross connections, we use MOS transistors. So the basic block diagram still has the decoder to ensure that only one of these rows can be active at any given time. However, now we are using a MOS transistor instead of a diode. So for the MOS transistor, this is specifically the NMOS transistor, all the source terminals of the NMOS transistor have been connected to ground. However, the drain terminals are pulled up to high voltage, right? They're all pulled up to high, the drain voltage. So source goes to ground, drain goes to high, and then we are controlling the gate voltage using the output of the decoder. So the same principle, we are still making sure that we still have that cross connection, or we don't, but we are now using the MOS transistors instead. So the address inputs would go all the way to the left. The decoder has active high outputs. It is going to make one of these rows active at any given address input, and if those lines, if this guy is on, that means that these transistors are going to be on as well. And when they are on, they are going to read a low voltage instead of a high voltage, because they are going to be conducting. Remember what we said when we were talking about NMOS transistor, when the transistors are on, the collector and drain terminals are essentially connected to each other. When the NMOS transistors are off, that's when there is an open circuit between those. And if we arrange this in this manner, the data that comes out of this would need to go into inverting buffers, just so that whenever you have a transistor, that indicates a 1 is being stored at that location, and absence of a MOS transistor indicates there's no 0 is stored at that particular location. So if the gate is on, voltage goes to, why aren't p-channel MOSFETs used pulling up the rail? You could, but all you would need is the decoder to have active low outputs in that case, right? So if you have active low outputs, then you can use all of this as p-channel MOSFETs. Absolutely. And that is exactly what, that's essentially what you do in one of the homework problems. Now using this, we will try to go through, let me clear this off here. We will try to go through two ROM structures that use transistors. One is the NOR based RAM and the other is a NAND based ROM. As usual, we will talk about what is the size of the ROM in this case. We have word lines that are going horizontally, and we have bit lines that are vertical. The word lines are essentially used to indicate the address, and the bit lines are supposed to indicate what is stored at that address. Yeah, Zach, you have absolutely the right point. You see, that's what we did here. For all the pull-up devices, we replace the resistors with p-channel MOSFETs that have their gate terminals connected to ground. That's already connected to ground, which means all of these are on by default. So what the next thing is the size of the ROM. So can you guys tell me what the size of the ROM is in this case? Four by 4, 16 by 4, 2 raised to 4 by 4, 16 by 4. Okay, so 4 by 4 is good, but there seems to be a confusion about why they would be. So let us go back to this particular example. In this case, we said this is 8 by 4, right? And we said this is 8 because this was 3, right? So 2 raised to 3 gave us 8. However, what we are looking at right now is not this, right? We are just looking at this particular structure there. So should I include 8 or should I include 3 in that number? You see, this 8 corresponds to number of word lines, right? And this corresponds to number of bit lines. So the address is 3-bit. However, the number of word lines are 8. The same thing that we saw over here. All the way at the top. When we had a 4-bit address, we had 16 word lines. And when we had 16 word lines, we said the size of this array would have been 16 by 4. So number of word lines by the number of bit lines. You guys see that? So if I go back here, what is the size of this? Number of word lines are 4 and the number of bit lines are 4. So the size of this ROM would be 4 by 4. So let's ask a preceding question then. How many bits, like number of address bits here, number of address bits? How many address bits would you need for this? That's right. So the number of address bits are 2, the number of word lines are 4, and at each word line you have 4 bits that are stored. Right? That's exactly what that is. Let us also talk about one-dimensional or two-dimensional decoding. So is this one-dimensional decoding or two-dimensional decoding? One-dimensional or two-dimensional? It is one-dimensional decoding. Because we are only decoding the rows. We are not decoding the columns. We just need to select one dimension here, which usually is the rows. So it's just one dimensional. Another way to figure that out is we have four bits at that location instead of 1. So it's still one-dimensional decoding. Now, let's go back and check about the word lines. Word lines themselves could be active low or they could be active high. Now, in this case, word lines are active high for a NOR-based ROM structure. So these lines that are coming out, they are coming out of a decoder which has active high outputs. And we know that only one of them can be active at any given time because these are outputs of a decoder. So let us ask the next question. What is stored at each location? What is stored at each address location? How many addresses do I need to? How many addresses would I need to track here, in terms of word lines? Well, the first case that you can have is word line 0 is active, everybody else is inactive, right? That's the first case. And then I would have to find what are the bit lines, corresponding bit lines. So what I'll do is I will create a table to the right in which I will have word lines represented in hex format as my input and the bit lines in hex format as my output. So the first possibility is word line 0 is active, word line 1, 2, and 3 are inactive. If that is the case, what would I need to write over here for word line represented in hex format? That would simply be a 1, right? You see, 0, 0, 0, 1. So the address or the word lines represented in hex format is going to be 1. What would be the next situation? The next situation would be, let us figure out this one first. Let us figure out what are the bit lines first. So tell me, if word line 0 is active, what happens to this particular transistor? Is it on or off? The first transistor, is it on or off? On. This guy is on, and I will just essentially just put a check mark on it. How about all the other NMOS transistors? All of them are off, right? So this guy is off, 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 off. Everybody is off. How about the PMOS transistors at the top? Are they on or off? They are all on. Perfect. Because I've connected the gate terminal of all those PMOS transistors to ground, essentially activating them. So that's what it is for word line 0 is active and everything else is inactive. That's what we have. Now let's also talk about why is this called a NOR based RAM? Why not some other name? Why NOR based RAM? Because the other option is using pull-up resistors. Pull-up resistors consume more power, a lot more power than the PMOS transistors. That is exactly the same reason why we did not construct logic gates using NMOS transistors. We constructed logic gates using CMOS transistors to save that power. Because you have the resistor, when current flows through that resistor, you are going to have power being consumed by that. Pull up, right? So pull up. Without the pull up resistor or pull up network, your bits cannot go to high. The whole purpose of pull up is to have the possibility that it can be high. And for the whole purpose of having a pull down is the possibility for that bit to be low. Otherwise, it cannot go high. All right, let's go back here and now talk about bit line. What is the bit line stored over here? Let's see, this guy is on. Oh, I asked a different question. I don't think we answered. Why is this called NOR based RAM? So for this, you might have to kind of recollect how, the transistors are connected in parallel. You see this? Each of these transistors is connected in parallel, which is exactly what we do for a NOR logic gate in the pull down network, right? In the NOR logic gate that we saw, in lecture 2 or 3, the pull down network had NMOS transistors in parallel. That's exactly what we have over here, which is the reason why it's called a NOR based ROM, the transistors being in parallel. We also have these things as ground, right? So let me highlight the ground lines here in green. That is a ground line there, and that is another ground line there. All right, let's go back and check. If this guy is active, what is bit line 0 going to read? Bit line 0 is connected to high, right? Straight away. So you are going to read a 1 over here. How about bit line 1? It is connected to ground. A 0. Perfect. How about bit line 3? Well, bit line 3 is always going to be high. Bit line 2 is always going to be high. Bit line 3. High again. You guys see that? So at that location 1 in hex, we have 1101 stored at that location, which is what? D in hex. I'm reading most significant to least significant. All right, let's go through this and fill out the table. What would be the next one I have to write? Let me erase all of these guys. Let me erase this, erase this, erase this. The next thing is going to be that, right? Word line 1 is active. If word line 1 is active, that is going to be 2. You are right. There are no inverting buffers. Let's check. When you have the bit, so in the previous case we had a 1 there, a 1 there, a 0 there, a 1 there, right? So the presence of the transistor made this a 0. So you will need output buffers in this case. I was going to talk about the output buffers like at the very end, but yes, you will need output buffers in this one. Bit lines will need to go to output inverting buffers. All right, let's go back here. All right, we are doing 2. So at 2, what do we have? Bit line 0 connected to, bit line 0 connected to high, low ground here. Let's use that 0 here. This guy is going to be what? Bit line 1. So directly connected to high. Bit line 2 connected to high. Bit line 3 connected to 0. Right. So 0, 1, 1, 0, you got 6. Next location 0, 0, 1, 0, which is what? 0, 1, 0, 0 is 4. At 4, what are the bits that are stored? No transistor, yes transistor, no transistor, yes transistor. So you've got 0, 1, flipped, 1, 0, 1, 0. What is that? What should I write over here? 5. Next one, well, the last one. 0, 0, 0, 1. This is easy, I suppose. There are no transistor present there, so you are going to get 1, 1, 1, 1. And that would be word line 3 is active, everybody else is inactive, so 8. And at 8 you have F stored. 5, yes, yes, yes. All right. Questions here, you guys. So with the NOR based ROM, we have looked at what is stored at each word line. You have looked at the fact that it is one dimensional decoding. We are going to need 2 address bits to have 4 word lines. And we looked at the size of the ROM. We filled out this table. And we also figured out that we need to have inverting buffers so that we can map the absence of a transistor to a 0 and presence of a transistor to a 1. In the next case, we will have a NAND based ROM. So for the NAND based ROM, I have the transistors are connected in series. As you can see, one after the other, right? They are all in series now, which is what we had for a NAND gate in the pull down network. For a NAND gate in the pull down network, we had 2 or NMOS transistors in series. That is exactly what we have over here. The difference is the word lines in this case are active low. We'll still do the size of the ROM. We'll still figure out whether it is one dimensional decoding or not. They are not in parallel, they are not in series, they are all independent, right? They are independent because these are bit line 0 is being read here, 1 here, 2 here, 3 here. So I wouldn't call it series or parallel, because well, I suppose you can call it parallel if you look at the entire structure. Another difference between NOR based and NAND based is where you monitor the bit lines. In the NOR based, you look at the bit line information over there. However, for the NAND based ROM, you are looking at those bits at the drain voltage of the drain terminals of the NMOS transistors. Again, even in this case, all the PMOS transistors are by default on. Oh, by the way, what is the size of the ROM? Still 4x4, right? 4 word lines, 4 bit lines. We are still doing one dimensional decoding. And we will try to have word lines here in hex. And we'll try to find out what is stored at each location in bit lines. So since the word lines in this particular structure are active low, we are going to have the first case as this guy is active, everybody else is inactive. So when word line 0 is active, 0, right, active, what happens to these transistors? Is this transistor on or off? Right. This guy is going to be off. And everything else is going to be on. So now let's try to see what bit line 0 is going to be. Is it going to be, it has two things, right? It can either be +5 or it can be connected to ground. It will be ground only when the transistors are connected, are allowing it to go to ground. So bit line 0, is it on, is it 1 or 0? Bit line BL0. Is at the same potential as the ground? Yes. How about bit line 1? You see, you would need both the transistors here to turn on for it to go to ground. It's not, right? This guy is off. So it would read 1. How about bit line 2? Always connected to ground. Bit line 3, also ground. So what do we have at the first address location? The first address location is 1110. What is that? E. At E, we have 0010 stored. That's 2. You guys see that? The only way bit lines can be pulled down to ground is if their pull down network has transistors that are all on, because they are in series. That's the only way it can go to ground. Or if there is a direct connection, like for the case of bit line 2. Now let's go to the other one. Erase. All of these go out. Our next case is, oh, by the way, do we need I should have done this, right? Do we need output buffers in this case, or we don't need any output buffers? Output inverting buffers, we don't need it, right? Because absent, present, absent, 0 1 0 0, right? So it is mapping exactly the way we want it to. So no need of output buffers, no need of inverting buffers. All right, let's go through to the next one. 0 comes here, everything else is 1. In this case, this guy is active, off, on, that's it. Bit line 0 cannot connect to ground. Bit line 1 can connect to ground. Bit line 2 always connected to ground. Bit line 3 cannot connect to ground. So you got 1001, which is 9. What is the address? 1101, which is D. At D, you have 9 being stored. Why is the word line address out of 4 bits when it is... Oh, so at each, for every address, so for every address 1011, right? For every address you will have word line, some word line active. And I'm considering over here which word line is going to be active or for every address combination. So the first thing I did was word line 0 was active. Now I'm doing word line 1 is active. So still the address bits are 2, but those 2 address bits will get decoded into one of the word lines being active. See that? All right, let's go through this. We did the second one. At D, we have 9 stored. Let's do the next one. 0 moves down here. Everything else is inactive. Off, everything else is on. Bit line 0 is connected to ground. Bit line 1 cannot be connected to ground. Bit line 2 is always connected to ground. Bit line 3 cannot be connected to ground. So 1. So 1010 at 1011. So 1011 is B and 1010 is A. Alright, the last particular combination here. Word line 3 is active, everybody else is inactive. This case, everybody is going to be on. So all the bit lines will read what? 0. And that address is what? 0, 1, 1, 1, that is 7. And at 7, you have 0 stored. And we talked about the fact that we don't have inverting buffers. There's no need for inverting buffers here. All right, questions about this. So we looked at two structures, NAND based ROM. We looked at how to identify the size of the ROM, figure out whether it is one-dimensional or two-dimensional decoding, and then we looked at the 4 word lines. We represented the word line information in hex, and we tried to figure out what is stored at those locations. So, so if you had to map, what we mapped is word line to bit line, right? But the word line themselves come from address bits. So the address bits, we are going to need 2 address bits. So 0, 0, when the address bits are 0, 0, you are going to be doing that. 0, 1, you are going to be doing that. 1, 0, you are going to do that. 1, 1, you are going to do that. See, so you still have 2 address bits. And add those 2 address bits, you have 4 bits that are stored. 2 in hex, 9 in hex, 8 in hex, 0 in hex. So data stored at the address. All right, questions here? Okay, so what I'll do is first I will stop recording